Hello, chemistry, and welcome to chapter 14, the gases. I can't believe it, but this is the last chapter we're going to be able to get through this year. So everything you guys have been doing is kind of building up to this. The second half of chapter 14 is going to be pretty tough, but this first half is not that bad at all. A little bit of math, actually quite a bit of math, but it's only multiplication and division. There's not really a lot of crazy conversions or anything like that. So 14.1 and 14.2, let's get into it. What we're actually going to do is I'm going to go over both chapters in this video and then go over example problems in a second video. Both sections in this video and go over example problems in the next video. That way you can just get all the conceptual stuff here and then watch the other video when you're doing your actual assignments. So let's look at the gas laws. There's three gas laws that we're going to go over, and the rest of the chapter is kind of built upon those three. But before we go there, we have to remember the kinetic molecular theory that we just went over in chapter 13. So let's go ahead and go over those real quick. Go over the concepts of the kinetic molecular theory. First off is that gas particles do not attract or repel each other. So we're assuming that when gas particles are running around inside a balloon or whatever, the particles themselves don't interact with each other. Like if they're near each other, there's no electric force and there's no gravitational force affecting anything that they're doing. In reality, yes, I guess it does, but in our theory, no, they do not interact with each other. Gas particles are much smaller than the distances between them. That is true. There's a lot of empty space in there, so how big a gas particle is extremely small compared to how big the empty space is. Step 3, gas particles are in constant random motion, so they're all moving in all sorts of different directions. They're spread out. They're going to move in a straight line until they hit something, whether that be another gas molecule or the container. And speaking of when they hit something, we see here, no kinetic energy is lost when the gas particles collide with each other or with the walls of their container. So what that means is we say it's completely elastic. No energy is lost. Everything is super bouncy, running around. If two of the gas particles hit each other, they just reflect off of each other and no energy is lost. As long as the temperature stays the same, the total kinetic energy of the system is going to stay the same as well. So no energy is just going to be lost like in the real world. And then we're going to say that all gases have the same average kinetic energy at a given temperature. So we're just saying all gases, regardless of what they're made of, all of them are going to have the same kinetic energy if they're at the same temperature. Not technically true. For example, hydrogen gas and a really heavy gas like sulfur hexafluoride, those two things have different masses. So if they have the same, if they have different masses, they might have different kinetic energies at different temperatures. So we do have to consider that. All gases have the same average kinetic energy at a given temperature. Oh, actually, no, that is true. What I was talking about was velocity. So yeah, what this is. They have the same average kinetic energy at a given temperature, that's fine. It says here, actual gases don't obey all those, but there's a decent amount of them that do. For a lot of the stuff that people do, if we assume all the stuff that we just read, their math is going to check out and everything's going to be fine. Now, obviously, for super sciencey people and for super specific processes, that is not going to be the case. But for a lot of stuff, it is. So let's look at the first thing. We got Boyle's law. We're going to look at the picture here while I read from the book. Robert Boyle was an Irish chemist from 1627 to 1691. He did experiments shown like what you see up here, studying the relationship between pressure and volume of a gas. He did a bunch of measurements, and he found out that if he doubled the pressure, he cut the volume in half. On the other hand, if he reduced the pressure by half, it doubled the volume. A relationship in which one variable increases as the other decreases is called inversely proportional. We can see what an inversely proportional graph looks like with that red line. So he was saying you squeeze this, and the pressure goes up, or you expand this and the pressure goes down. So as one gets larger, the other one is getting smaller. And that's an inversely proportional graph. So eventually he put this all together in something called Boyle's law. States that the volume of a given amount of gas held at a constant temperature varies inversely with the pressure. And this is what this looks like in terms of math right here. I can't actually highlight it. That's what it looks like in terms of math. Okay? The products of pressures times volume for any two sets of conditions are always equal. So Boyle's law can be expressed by P1 V1 equals P2 V2. That means if you start out with a certain pressure and a volume, and you change the pressure, then this volume is also going to change. But since they're inversely proportional, if you raise the pressure, that means the volume has to go down. Or on the flip side, if you lower the pressure, that means the volume has to go up. They are inversely proportional. They do the opposite. So we see that here. If this is our normal, if this middle one is like normal, we can say, as we squeeze this, as we compress it down, we see there's less volume from 5 liters to 2.5 liters, but there's a lot more pressure, 4 atmospheres compared to 2 atmospheres. On the other side, if we release this a bit, we go from 5 liters to 10 liters, then we see that this atmosphere actually decreases. So we get more volume, but less atmosphere, less pressure. And that makes sense even if you're just looking at this. It's the same amount of little particles, but down here, they're all smacking the sides of the container a lot faster than they are over here. So this should have more pressure than that. And if we follow this graph, that's exactly what that is saying. As you increase the pressure, the volume goes down. So as you go to the right, the graph goes down. And that's what that's saying. So that's Boyle's law. Next up is one that you guys are probably familiar with as well. Boyle's law, I think you guys probably get pretty easily. Same thing with this one. I don't know if you know, but because we don't really have weather, but the book uses an example of, have you ever noticed that on a cold day, a tire on a car might look as if it's low on air? However, once you drive it for a while, the tire warms up and the tire looks less flat. Personally, I don't care about cars that much, so I don't pay attention to this, but maybe some of you have. This is an example of Charles's law. So the French physicist, Charles is his last name, from 1746 to 1823 studied the relationship between volume and temperature. In his experiments, he observed that as temperature increases, so does the volume of a gas if the pressure gets to stay constant. So he did a little example like this. He put this under 1 atmosphere pressure, he then heated it up, and he allowed this piston to move freely. So the gas particles push the piston up to keep the same pressure. But what that means is as you increase the temperature, you increase the volume. Notice that we said increase both times. Last time we were saying as one increases, the other one decreases. This time we're saying if you increase the pressure, if you increase the temperature, you increase the volume. That is something we call directly proportional. Okay? It is directly proportional only if we have to if we change stuff around. So if you look here, it's not necessarily going to 0. This should be 0. The reason why it doesn't is because this temperature scale of Celsius doesn't make sense for our math problems in this chapter. Instead, we're going to have to switch over to Kelvin. Because in the Kelvin scale, 0 kelvins means there's no temperature, which conceptually almost doesn't make any sense, but what it means is that no particles are ever moving ever again. So if we switch our temperature scale over to Kelvin, now this graph is what we call directly proportional. Okay? Because they both start at 0, and as one gets bigger, so does the other one. As you go to the right, the graph goes up. So as you increase temperature, you increase volume. We can write that in terms of V1 over T1. And any two sets of conditions, just like the last one, is the same thing. So V1 over T1 equals V2 over T2. Just always remember, we need to be using Kelvin instead of Celsius. And it's simple. The way you do that, you just add 273 to Celsius, and that gets you the Kelvin, how many kelvins something is. So not too complicated, just an addition problem to get the right temperature. And the last out of these three gas laws is Gay-Lussac's law. Not as easily seen, I guess. What this law is, it relates pressure and temperature. He found that a direct proportion exists between the Kelvin temperature and the pressure. Gay-Lussac's law states that the pressure of a given mass of gas varies directly with the Kelvin temperature when the volume remains constant. It can be expressed mathematically as P1 over T1 equals P2 over T2. So the first set of conditions has to equal the second set of conditions. This one is also directly proportional, so if you start with 0 and you go to the right, then the graph goes up just as well. Notice we're also in Kelvin again, because we don't use Celsius when we're talking about this stuff. We only use Kelvin. This can be explained, or this can be shown in the reason why like cans of hairspray and spray paint and stuff say don't leave in a hot car, because the volume is staying the same, but as the temperature increases, the pressure is going to increase. And eventually that pressure is going to get so high that it's going to break the container and explode. And that's no good. Same thing with like a pressure cooker, works under the same conditions. That's all of 14.1. 14.2 then says, well, what happens if we just put all those together? Because if we just take away this, if we just look at this top right here, P1, V1, P2, V2, that's just Boyle's law. And if we ignore pressure, then that's just Charles's law. And if we ignore volume, then that's just Gay-Lussac's law. So we can smush all of them together and just use this equation for everything. All three variables have the same relationship to each other as they have in other gas laws. Okay? So you can always use this one, it's just sometimes we don't need to. For example, if the problem says the temperature stays constant, we don't need to even consider temperature. All we would have to do is use this top line, right? So we default back to Charles's law. So that's why they don't show you this at first, because they're saying, hey, look, you can take this step by step, but if all three are changing, then we can use this equation to tackle everything. And that's what you'll see in this example problem once you watch the other video. This last little bit is kind of a side note, and this is Avogadro's principle. So that same Avogadro that gave us the mole, he found out that equal volumes of gases at the same temperature and pressure contain equal numbers of particles. Let's say that again. Equal volumes of gases at the same temperature and pressure contain equal number of particles. So it doesn't matter what kind of gas we're talking about. If it's the same volume at the same temperature and the same pressure, it's the same exact amount of gas particles in there. Heavy particles, small particles, it doesn't matter, it's always the same. And that's Avogadro's principle. If you can guess, it does have something to do with a mole. And the molar volume for a gas is the volume that 1 mole occupies at 0 degrees Celsius and 1 atmosphere of pressure. All right, so if it's 0 degrees Celsius and there's 1 atmosphere of pressure on a container, and there's a gas in there, we know how many particles of gas are in there. There's 1 mole of it. So similar to how every element has a molar mass, every gas has a molar volume. But the fun thing about molar volume is that they are all exactly the same. All gases, doesn't matter what it is, all gases at standard temperature and pressure, which is 0 degrees Celsius and 1 atmosphere of pressure, all gases under those conditions take up 22.4 liters for every 1 mole. Okay? So that is a super useful conversion factor for this kind of stuff. No matter what kind of gas it is, you don't even have to look at the periodic table, it doesn't matter. If it's a gas at 0 degrees Celsius and 1 atmosphere of pressure, it takes up 22.4 liters for every 1 mole of that gas. That makes our math a lot easier, because you don't have to go and find a molar volume for every single element like you do molar mass. Instead, you just check the temperature and pressure, standard temperature and pressure. All right, that means the volume is 22.4 liters, and that's it. Easy. And that's actually it for section 14.1 and 14.2 as well. So we're good there too.